The last piece of Chapter 1, Section 1.3, is about experiments and observational studies. And the main thing that we are trying to get at here is whether we can say something about correlation or association, or whether we can say something about causation. So causation would be if we could say, this causes that. Heat causes the snow to melt. That is really hard to prove, and almost never, well, no, I shouldn't say that. Many times in this class, we are not going to be able to prove causation. So the most important thing to know is that correlation is not equal to causation. And correlation, another word for it is association. So causation, really hard to prove. Association, that one is easier. And association or correlation is when values of one variable tend to be related to values of another variable. So for example, people's height and weight tend to be associated with one another. If you're taller, you probably also weigh more, but there's lots of variability in people's heights and weights. So the association is not perfect, but we can see that there is a relationship there. So I'd like us to think about some headlines that I pulled off of the news here. A lot of times headlines try to imply a causal relationship, and it might not be legitimately causal. So that's what we're going to be thinking about. We're also going to be reviewing the idea of explanatory and response variables. So here are three headlines. One is, "The Super Bowl is coming and we're running out of chicken wings." The next one, "Proved the more you exercise, the better it is for heart health, new study finds." And "Where do dogs have the healthiest teeth and brightest smiles? Whimsies unveils list of smiliest dog cities in America." I'd like you to think about the explanatory and response variables that are implied in each of these three headlines, and then see if there's an implied causal relationship and whether or not you think that is legitimately causal. I think I will talk just about the first one here. So let's think about the explanatory and response variables. Like I said in the last video, I usually think about my response variable first. That's a little bit easier for me to think about. So in this case, I think the response is the number of chicken wings that are available. Maybe in the United States, that's my guess. And the explanatory is the proximity in time of the Super Bowl. So we think that the proximity in time of the Super Bowl might explain something about the number of chicken wings that are available in the United States. And so then the question is there an implied causal relationship? And I think yes, there's an implied. There's not really a word that I can point to in this sentence that implies that causal relationship, but the sort of putting those two things together, it makes me feel like they're trying to imply that. And do I think it's legitimately causal that the Super Bowl coming would mean that we would be running out of chicken wings? I could sort of see the explanation either way. So let's say legit and not legit. The legitimate would be, people like to eat chicken wings while they're watching sports games. So that might make sense to me that it would be causal. But then not legitimate, I don't know that people are stocking up on their chicken wings for the Super Bowl right now. If it was me and I was hosting a party, which I'm not going to do, the thing that I would do is probably go out shopping a couple days before the game, a week before maximum. So I probably wouldn't be, 3 weeks before and 4 weeks before trying to buy it up. So there might be something else going on here. Those two things are happening at the same time, but they're not causally related. So not legit. People probably don't slowly stock up. So maybe there's not this sort of relationship of, as time progresses, the number of chicken wings goes down. There could be something else going on. And we can talk about the other two in synchronous class. So let's think about a few more examples. This is from a Center for Wellbeing, and they're reporting on some associated change in well-being based on some things that you might do in your life. So they're saying that more time spent listening to music is associated with a decrease in depressive symptoms, an increase in life satisfaction, and a lagged decrease in depression. So right now less, and then also in the future less. So there's sort of an implied causal relationship there. Browsing the internet has these, increase in depressive symptoms that it's associated with. Watching movies, right? Then we get down to communicating virtually with friends and family. And it's gone down off the bottom of my screen here, but it's associated with an increase in life satisfaction. But then I can also see that it is associated with an increase in anxiety and also a decrease in life satisfaction. So it's associated both with something positive and with some negative things. And so that, I think, really calls into question the possibility of there being a causal relationship because it's associated with both things. And even these associations that are just with something positive or just with something negative, we don't know which the direction of causality is. So it is possible that listening to music leads to less depression. But it's also possible that less depression means that you have more interest in doing things that you like, and so that leads to listening to music. So just because there is an association between two things, like listening to music and a decrease in depression, doesn't mean that this is the direction of that association. It could be that when you have less depressive symptoms, you listen to the radio more. And the same sorts of things. Maybe if you have an increase in anxiety, maybe that leads you to reach out to your friends and family, and maybe that leads to an increase of life satisfaction, or maybe communicating virtually actually decreases your life satisfaction. So just because we have these associations, we don't know the directionality of the causation. And then there's also this idea of a confounding variable. So a confounding variable is a third variable that we maybe weren't initially thinking about that is associated with both the explanatory and the response variable. And we will sometimes draw little diagrams to help us show some of these relationships. So for example, a classic one is ice cream sales and deaths by drowning. Those two things are associated. And so, the question is it that more ice cream sales lead to more deaths by drowning? More deaths by drowning lead to more ice cream sales? Well, no, it's actually neither. It is the season. So the season probably drives ice cream sales, and the season probably drives deaths by drowning, and there's actually no relationship here in between these two things. They're not causally related, even though they are associated. So just because you see an association doesn't mean that there's a relationship in either direction, and there could be this third thing, which we would call a confounding variable. So I'd like you to try to think of a possible confounding variable in each of these situations. Places with more malls tend to have more doctors. People who have multiple winter coats are more likely to break their arm. Students who attend class get better grades. And private school students tend to have better mental health than public school students. So give those a little bit of thought. The first one, places with more malls tend to have more doctors. The confounder is the size of the city. So bigger cities probably have more malls, and they also have more doctors. So something about the size of the city, the population density, something like that. And again, how about you think about those other three, and we'll talk about them when we get to synchronous class. Okay, so we've been talking about association. Association does not imply causation, but we often want to find some type of causal relationship. And the way that we can assess a causal relationship is by doing an experiment. So we break down studies into observational studies and experiments. So an observational study is one where the researcher doesn't control anything. They just observe things as they currently are. And an experiment is where a researcher does actively control the value of one or more of the variables. So they change something about the situation so that they can see if that has an effect. So observational studies often have confounding variables because you're not controlling for anything, and they can almost never be used to prove causality. So as an example, it took a very long time to find that there was a causal relationship between smoking and lung cancer because it wasn't ethical to do an experiment, to say we are going to decide that you smoke and you don't smoke, and then we'll see what happens to your cancer outcomes. People just had to observe the world how it was. And it was possible that there was some confounding variable. Many researchers actually argued that for a long time, and so it was very difficult for them to prove causality. So in occasional cases you can do it, but almost never. So how do we avoid confounding variables when we run experiments? We randomize. So we randomly assign people into groups, and then we know that there can't be anything particular confounding because we are the one who just randomly decided what was going to happen to the observational unit. So the gold standard, if you want to make inference to draw a causal conclusion, is a randomized experiment. So that's the one where an explanatory variable for every observational unit is randomly determined before the response is measured. So maybe we want to know if looking at trees makes people feel more calm. We get a group of people together, we randomly decide that some of them are going to look at trees, some of them are not, and then we have them do whatever they're going to do, and then we measure their calmness afterward. We call those different levels of that explanatory variable treatments. So in the case where I was just talking about thinking about trees and calmness, maybe looking at pictures of trees or looking at actual trees would be the treatment, and the control would be just doing nothing. But there could also be multiple treatments, looking at a picture of a tree, going outside and looking at a real tree, or doing nothing. So you can have more than one treatment. And so the question is, if we have this gold standard where if we have a random experiment, we can make inference, why don't we always randomize? And the reason is sometimes it's not ethical or possible to run a randomized experiment. Again, we couldn't force people to smoke or not smoke to determine the outcome on cancer. So it wasn't possible to run a randomized experiment. And in those cases, you need to do the best you can with observational data. And that usually means just stating that there is an association. So the bottom line here, correlation is not causation, but all causation is correlation. So if you want to see if there's a causal relationship, you need to have some association between the variables. If there's no association, well, there can't possibly be causation. Randomized experiments are the gold standard, but sometimes you have to do the best you can with an observational study, and those observational studies might have confounding variables, so you need to not make causal statements from them.